In this video, I'm going to be showing you how I like to draw the natural amino acids, representing them in a fully protonated state. But if you're interested in watching how we can modify these structures to be representative at a particular pH, I highly recommend that you watch the follow-up video that goes through that process. And as a disclaimer, this is the way that I like to draw the structures, but it certainly is not the only way to represent these amino acids. We can use the alphabet as single letter code for each of the amino acids, where A is the single letter code for alanine that has three-letter code ALA. And we're going to be seeing that each of these structures has a common amino acid backbone. And this backbone consists of an amino group, where in addition to being covalently attached to these three hydrogens, the nitrogen atom is attached to a carbon that we call the C alpha, also called Ca, or alpha carbon. Because this nitrogen has 4 covalent bonds, it is going to have a positive charge. The C alpha will come back to in just one moment. It is followed by another carbon that is a member of a carboxylic acid functional group. A carboxylic acid has a carbonyl and an alcohol to make that functional group. So if we look at this backbone, we see that we have the amino group and carboxylic acid group, hence the term amino acid. The alpha carbon is between those two functional groups here. And what we'll see is that for each structure, the key difference is going to be the substituent attached to the alpha carbon. So we can call those R groups or side chains, and I'll use both of those terms throughout this video. In the case of alanine, the R group is a methyl group. And so using our Greek alphabet, we had the C alpha here, so that makes the methyl carbon the C beta. I just want to take one moment here to highlight the backbone that I'm going to be reproducing over and over again throughout this video, just to emphasize that this is shared across all of the unique amino acids. B does not represent a naturally occurring amino acid, so we'll go to cysteine, or C, that has three-letter code CYS. So we'll start off by drawing the backbone, the amino group, the alpha carbon, and carboxylic acid. The side chain is going to be attached to this C alpha. So we have the C alpha, a C beta, and a sulfhydryl group. So cysteine is a nice polar amino acid. D is for aspartic acid, or ASP. Reproducing our backbone to have the amino group, alpha carbon, and carboxylic acid, the side chain of aspartic acid is going to have a carboxylic acid in it. So we have the alpha carbon, beta carbon, and at the gamma carbon is where we see the carboxylic acid. E is for glutamic acid. And it has three-letter code GLU, which some people like to remember the three-letter code and single-letter code because they represent the word glue when you put them together. As its name suggests, we're also going to see a carboxylic acid in its side chain. So I've just put up the backbone. And so we have the alpha carbon, beta carbon, gamma carbon, and at the delta carbon is where we see the carboxylic acid. You may be looking at these structures and saying aspartic acid and glutamic acid look really similar. But the key difference here is that we have one more CH2 in glutamic acid than we do in aspartic acid. F is for phenylalanine, which has three-letter code PHE. You may be noticing that alanine is not a completely new name, that we used that in our first amino acid. And so you could actually use that to your advantage to draw alanine as your starting point for phenylalanine. So we have the backbone and the methyl group that make up alanine. And now we're going to incorporate the phenyl component of the name by drawing our ring here. And so you could use the circle to represent the aromaticity there, or we can also just directly draw the double bonds. G is for glycine, and that has three-letter code GLY. This is our simplest amino acid because its R group is a hydrogen. So because that is the case, we're done drawing glycine. H is for histidine, which has three-letter code HIS or HIS. We'll start off with our backbone again. And so we have the alpha carbon, the beta carbon, and the gamma carbon is where we see a five-membered ring. And so this ring is also the structure of imidazole. And we're going to include double bonds as well in this side chain. Now, we'll notice that this nitrogen has 1, 2, 3 bonds, one to the hydrogen and two more to carbon atoms. But this nitrogen has 4 covalent bonds. So in a fully protonated state, it would be positive in charge. One way that you might remember how to draw the structure of histidine is that we have carbon, nitrogen, carbon, nitrogen, carbon. So that might be a pattern that's useful as you repeat your drawings. I is for isoleucine, which has three-letter code ILE. We see the amino group, alpha carbon, and carboxylic acid as the backbone. And from that alpha carbon, we'll have a beta carbon, gamma carbon 1, gamma carbon 2, and delta carbon. I like to look at this structure as if to say that it looks somewhat like an I, a capital I, but is missing the other arm. J is not representative of a natural amino acid, so that brings us to K, which is for lysine, which has three-letter code LYS. Lysine is a positively charged amino acid based on its side chain identity, which is going to involve the alpha carbon, beta carbon, gamma carbon, delta carbon, and epsilon carbon. This is the last carbon that's part of the chain, and it is attached to an amino group, which is where positive charge comes into play for the side chain. L is for leucine, which has three-letter code LEU. We'll start off with the backbone again. Leucine is going to have a beta carbon, gamma carbon, and 2 delta carbons. To me, leucine looks like it has 2 L's in its side chain. M is for methionine, the second sulfur-containing side chain, and has three-letter code MET. So we are reproducing our backbone, and we have our beta carbon, gamma carbon. This is followed by the sulfur and has a final methyl group. So loosely, this looks like a capital M on the side chain. N is for asparagine, which has three-letter code ASN. We have the amino group, alpha carbon, and carboxylic acid, where asparagine is going to have the alpha carbon, beta carbon, and the gamma carbon is where we're going to see an amide functional group. So this is really similar to aspartic acid, but instead of having a carboxylic acid in the side chain, we have an amide. O does not represent a naturally occurring amino acid, so that brings us to P for proline, which has three-letter code PRO. Now, proline is a unique amino acid in that it is cyclic, but we can start off with our common backbone. And what we'll see is that there's a five-membered ring between the alpha carbon and amino group. So we have our beta carbon, gamma carbon, delta carbon, and back to our nitrogen to give us 1, 2, 3, 4, and 5 members of this ring. But one thing we do need to adjust here is that this nitrogen has too many bonds now. So instead of NH3, it's NH2, so that it has 1, 2, 3, 4 bonds. And that is our structure of proline. Q is for glutamine, or GLN as our three-letter code. So starting off with our backbone, we're going to have our side chain extending from our alpha carbon, beta carbon, gamma carbon, and at delta is where we're going to see our amide functional group. So glutamine and glutamic acid are very similar, and the key difference is that instead of having an amide here, glutamic acid has a carboxylic acid functional group on the side chain. R is for arginine and has three-letter code ARG. We'll start off again with our backbone. And the side chain consists of the alpha carbon extending to beta, gamma, and delta carbon. And from that delta carbon is going to be an NH that is followed by another carbon, which has a double bond to NH2 that has a positive charge, and a single bond to NH2 on the other side. So this is another basic or positively charged amino acid. S is for serine and has three-letter code SER. We have the backbone one more time. And serine has the alpha carbon going to the beta carbon and an alcohol. So it's almost identical to cysteine, except it has an oxygen here instead of a sulfur. T is single letter code for threonine, or THR as our three-letter code. And threonine is going to incorporate the backbone that is essentially going to be an extension of serine. So if we draw serine, we just have a methyl group. So if we see the alpha carbon, beta carbon, and gamma carbon. One other way that you might remember the structure of threonine is that it sort of looks like a T. So this threonine and serine are also polar amino acids with regard to their side chains. U does not represent a naturally occurring amino acid. So we go to V for valine and has three-letter code VAL. Starting off with our amino acid backbone, valine has the alpha carbon, beta carbon, and two gamma carbons. It looks like an upside down V. W is for tryptophan, one of our aromatic amino acids, and has three-letter code TRP. Starting off with the backbone, we have the alpha carbon, beta carbon, and at gamma, we're going to see a ring structure begin. So we have a 5-membered ring that is part of a bicyclic aromatic structure to a 6-membered ring. So we can incorporate double bonds appropriately there. X does not correspond to a naturally occurring amino acid, but Y does. Y is for tyrosine, or TYR. We have the amino group, alpha carbon and carboxylic acid as our backbone. Tyrosine is essentially an extension from phenylalanine. So if we draw the structure, this is phenylalanine. The key difference is the addition of an alcohol at the para position. So the para position has an alcohol. And last is Z, that does not represent a naturally occurring amino acid. So one other mnemonic that might be useful is that the unused letters can give you U box JZ as a reminder for which letters do not give rise to single letter code for amino acids. And that's how I like to draw the 20 naturally occurring amino acids. If you want to see how these structures get modified as you take pH into consideration, feel free to visit the follow-up video.